So I'd like to welcome Prakash Panagaden, the second speaker in our online seminar. I've known Prakash for a long time, ever since I started getting interested in category theory. I've been meeting him now and then and talking to him, and now that I'm much more interested in it, I seem to be talking to him more, and he's been doing lots of really interesting stuff combining category theory, probability theory, and analysis, which is a blend I find very interesting because it hasn't really been explored as much as it should yet. So it's great to see him diving in there and discovering all the nice things first. So go ahead, Prakash.
Great. Well, thanks for that introduction, John. Indeed, as John mentioned, I've been interested in, well, actually, I'm interested in probability theory, but I have found category theory to be a very useful organizing viewpoint on many things. So the topic I'm talking about today, a categorical view of conditional expectation, is actually a piece pulled out of a much larger work, which I'll tell you about in a second. And what we were trying to do is to formulate the notion of conditional expectation along a generic morphism. And why we did this, I'll tell you also in a minute. So here's a kind of overview of what I plan to cover after some introductory remarks. I'll give you some background in functional analysis, which most of you probably know. Then I'll say something about cones, which may be less familiar, and then specifically certain cones of measures and functions that arise in this work. And then I will also say a bit more about conditional expectation, and then I'll talk about the setting in which all this happens. There are a pair of categories that need to be introduced. And then finally, I'll introduce the expectation value functors, and I will conclude with conclusions, I guess. Anyway, so this is joint work with my former master's student, Philippe Chaput, Vincent Danos in Paris, and Gordon Plotkin in Edinburgh. This paper appeared in 2014. The citation is there. And it took 5 years to get through the refereeing process. So the original conference version was from 2009. I should mention that this idea of functorializing conditional expectation is due primarily to Vincent Danos. So let me say very elementary things about this setting. We have a probability triple, which is a sample space omega, a sigma algebra defined on it, sigma, and a probability measure p. And this describes some kind of random process which produces outcomes in omega distributed according to p. So what that means is that if little omega is the outcome and capital A is one of the measurable sets to which you can assign a probability, then the probability that this outcome actually lies in the set A is exactly what P of A tells you. Now, supposing I know in addition that omega actually lies in a set B, which is another measurable set, then we'd like to reassess our probability that omega is in A. And this is the well-known concept called conditional probability, the probability of A given B, denoted by this vertical bar notation. And it has this more or less elementary formula, which says, obviously it has to be in both A and B, and then you normalize by the total probability mass of B. Of course, this formula is simple and intuitive. It clearly doesn't work if B has measure 0. So one has to actually adopt a more sophisticated point of view in that case. So what is actually happening is that we know whether omega is in B or B complement. And so we can compute the probability of A given B and also the probability of A given B complement. And we can define a function that is basically constant on B and on B complement and just returns one of these two numbers. But still, it has now become a function that takes on values depending on whether you're in B or B complement. What is this collection B, B complement, empty set, and the whole space? Well, it's actually a tiny little sigma algebra. So supposing I look at a slightly larger sigma algebra generated by a countable partition of omega, then we can define a function which basically is constant on each set of this basic partition, and it tells you the conditional probability for each one of those possible outcomes, whether it lies in one of those sets. So pushing this idea a bit further, you see now we've gone from the conditional probability just being a number to it being a function. or a random variable. And now we can look at the most general situation. We are now given a sub-sigma algebra of the original sigma algebra. And for every set in that sub-sigma algebra, we are told whether or not B lies in that set. So this is a lot more partial information. And now what we would like to do is to say, okay, I want to reevaluate all my probability estimates in view of all this additional information that I have been given. So one should think of these sigma algebras as kind of describing one's view of what one can see of the sample space. So basically everything that's in the sub-sigma algebra lambda has been utterly revealed to you. But now, of course, there are probably many more measurable sets in the larger sigma algebra sigma, and you need to revise how you compute those probabilities. So we will define a random variable, and not just a number, a random variable, p of a given lambda, which is a lambda measurable function. And for every measurable set p in lambda, I can compute the probability of a and b by integrating that random variable over b with respect to the measure p. So this is the sort of the highest point of conditional probability, the most general situation where you are conditioning with respect to a sub-sigma algebra. One can do the analogous thing with expectations. So you have a sample space, you have a random variable, you compute the expectation, of course, in the obvious way. And now, as before, you want to revise the expectation value based on new information about where the possible outcomes may lie. So once again, in the most general setting, you're conditioning on a sub-sigma algebra, and you can now define the conditional expectation of f given lambda as a lambda measurable function such that for any set in lambda, you can compute the expectation value by integrating this new random variable instead of integrating f. You might look at this formula and say, this is a bit silly. Why can't I just take f itself to be this random variable? Well, the point is, this new random variable is required to be only lambda measurable. And lambda is a much smaller, well, I didn't mean much, but at least smaller sigma algebra. So it is smoother in some sense. It doesn't see variations that are not visible to the lambda algebra. So in some sense, what has happened is that this very fine function f, whose expectation value you're trying to compute, has been replaced by this much smoother and hopefully more tractable function, which is only lambda measurable instead of sigma measurable. Okay, so that's the background setting. And now I need to introduce some functional analysis background in order to describe all the things that are going to happen. So Banach spaces are simply normed vector spaces. So that's a vector space equipped with the norm satisfying the usual norm axioms. As normally, a norm induces a metric and hence a topology. And if the norm happens to be, if the vector space happens to be complete in this metric induced through the norm, it is called a Banach space. A linear map between Banach spaces is said to be bounded if there exists a positive real number that kind of bounds how much the norm can be blown up by that linear map. And there's a basic fact in functional analysis, possibly the first exercise you do when you're learning this subject, is that a linear map between normed spaces is continuous if and only if it is bounded. And by continuous here, I mean in the norm topology. So given a bounded map between these normed spaces, the map itself can be assigned a norm by taking the soup over all the norms of the vectors that you get by applying T to vectors of norm 1. This is a norm on the space of bounded linear maps, and it is sometimes called the operator norm. And with this norm, the space of bounded linear maps between Banach spaces itself forms a Banach space. So that means complete with respect to this norm. Now there's a beautiful concept called duality. So the space of bounded linear maps from V to, let's say, R is itself a Banach space. Quite often people work with the complexes, but since I'm interested in probability, I'm going to look at R. So this is called the dual space, which I'll write V star. Now, given two vector spaces, we say that they are an algebraic duality if there's a bilinear form of this type shown, such that the spaces of functionals separate points of U and V. So what I mean by that is, if I fix a vector in U, and then let the other argument vary across V. I've induced a functional from V to R. That functional should separate points, and dually for the other one.
I'm going to interrupt. There's a question which is back when you said that the space of maps between Banach spaces is itself a Banach space. They were asking, is there a tensor product of Banach spaces that makes this be a closed monoidal category? Because this looks like an internal, like it wants to be an internal Hom.
Well, there are 14 tensor products on Banach spaces.
Right. Well,
as explored by Grothendieck. So I think I'm not sure is the short answer to that, but I think one of them, possibly the projective tensor product, does give it a closed structure, but I don't think it's for all Banach spaces. Maybe only with contractive maps.
Okay, yeah, these questions that seem very natural from a category theoretic point of view, often they are rather tricky in these analysis
yes,
contexts.
So especially in the Banach space setting, these are rather tricky. Like, so you might think, well, for Hilbert spaces, it's kind of it's fairly clear what the tensor product should be. But then for Banach spaces, as Grothendieck showed, there are 14 different ones. And exactly which one does what, I don't remember.
Okay.
Okay, so we were talking about duality. So, all right, so duality is so this concept of algebraic duality is mediated by the existence of a bilinear form that's sufficiently rich as to be able to see the distinction between different points. Now we'll say two Banach spaces are in duality, a somewhat peculiar terminology, if the functionals you get by choosing different elements of V and letting it vary over the other argument vary over U gives you a subset of the bounded linear maps on U, and similarly for V. So for any Banach space, if you look at V and V star, these are of course naturally in duality because the pairing is simply the bilinear form that you get by saying apply the thing in V star to the thing in V. And it's very easy to see that this gives you a notion of two spaces being in duality. There is a canonical injection between a Banach space and its double dual. Now, if this happens to be an isometry, then we say that the Banach space is reflexive. So that means it looks like it's double dual. Now, for ordinary finite dimensional vector spaces, we are very much used to the fact that these things are always isomorphic. And even for Hilbert spaces, this is true. But for infinite dimensional Banach spaces, these are not necessarily reflexive. And this is, again, highly technically difficult subject to sort out because some spaces are and some are not. And sorting out exactly which ones are which earned people like Tim Gower's Fields medals. So certainly I don't want to delve too much into exactly when things are reflexive. Finite dimensional ones, of course, are always reflexive. So now let's look at some concrete Banach spaces. If you have a measure space and you have integration defined on it, then we define the usual notion of a function being integrable if its integral is finite. I don't know why I wrote dx there, that should have been d mu. So if two functions agree everywhere except on a set of mu measures 0, their integrals will be equal, and in fact we will identify them. So even though we are going to define LP as a kind of function space, it actually isn't. It's equivalence classes of functions. And these functions may differ in quite a lot of places, except that these quite a lot of places will have measure 0. So the integral defines a norm on these equivalence classes and gives a Banach space L1 x sigma mu. I'll just write L1 of mu because it's the measure that's important. And analogously, you can, instead of taking the integral of f, you can take f raised to the power p, integrate that, and then take the pth root. You get a space called LP. You can even define an L infinity by looking at an upper bound. So if you look at bounded functions, and then you look at the smallest upper bound, that gives you a norm. Now again, when I say upper bound, I mean mu almost everywhere upper bound. So I'm allowed to cross that upper bound, but only on a set of measures 0. So this space is called L infinity. Again, it's an equivalence class. And so again, one cannot really technically view these things as functions, but casually we almost always think of them as functions. Okay, again, L infinity is a Banach space with the norm being given by the inf of all the possible upper bounds. And these are all Banach spaces. Now, the duality theory for Banach spaces is very pretty. It says that if P and Q satisfy this so-called holder relationship, then LP and LQ are duals of each other. So if P is 2, then Q is also 2, and you get L2, which is self-dual, and that's of course not just a Banach space, but a Hilbert space. However, L1 and L infinity are not duals. The dual of L1 is indeed L infinity, but the other way around is not the case. I actually was trying to look up when exactly what is the dual of L infinity. It turns out to be rather a complicated gadget, and I don't want to get into it here. You might be interested in seeing an example of something that's in L infinity, but not L1 star. Sorry, I mean the other way around. And it turns out such examples are not easy to give. It depends on the axiom of choice, in fact. So we will switch to a cone view and the situation will be dramatically improved. So what exactly are these cones? We want to combine linear structure with order structure. So if you have a vector space with an order, and with an order I mean it interacts nicely with the vector space operations, then we have a natural notion of being positive or negative, x being greater than 0, and this 0 is of course the 0 of the vector space. Then we will say x is a positive vector. And what properties does the collection of positive vectors have? So certainly we'll include 0 amongst our positive vectors. It turns out that if you take a positive vector and multiply it by any positive real, then it will stay positive. The sum of any two positive vectors is positive. And if a vector and its negative are both amongst your positive vectors, well, then that vector better be 0. Okay, so there are many variations of the definition of cone that I have seen, some of which don't have this third axiom, but these are the ones I'm sticking with. Now we define a cone in a vector space to be a set of vectors satisfying exactly these closure conditions. So if you have an order, the set of positive vectors is indeed a cone. Conversely, if you have a cone, you can actually define an order by saying u is less than v if v minus u is in the cone. So having a cone and having a partial order on the vector space are equivalent concepts. Many of the structures...
I think it needs to be an order that gets along with addition, right? A partial order.
Yes.
Yeah.
So I said that the order interacts well with the vector space structure.
Sorry.
Definitely. Otherwise, anything can happen. So many of the structures that we want to look at are indeed cones, but are not necessarily part of any obvious vector space. So for example, the collection of measures on a space, well, that has a natural cone structure, but it's not really part of a vector space, though of course you could artificially embed them in a vector space, for example, by introducing signed measures. And perhaps some of you could argue passionately that that's not artificial, but let's leave it like that. Indeed, many people who used to work with cones are now switching to vector spaces with orders and using Reed's lattices instead, but I'm sticking with cones for now. So this is an axiomatization of the abstract concept of cone. So rather than cone being embedded in a vector space, I learned this from Selinger, but I imagine that many people have independently invented this. So here I'm going to define a cone as simply a commutative monoid. So it has a plus operation and a 0 with an action of the non-negative reals with the usual distributive law of addition and multiplication. And the following important cancellation law, which has to be stated like this because we don't have negatives anymore. And we'll also have the following strictness property. If v plus w is 0, then both of them have to be 0. Every cone comes with a natural order structure automatically. So we're going to say that u is less than v if there's some element w in the cone such that u plus w is equal to v. One can introduce a notion of a normed cone by introducing the standard norm axioms, again requiring proper interaction with plus and with the order. Now, normally one uses norms to talk about convergence of Cauchy sequences so that one can then talk about completeness. But without negation, how can we talk about Cauchy sequences? So I'm going to actually write ui minus uj, and then that will, but what I'm really going to mean is that the unique w such that uj plus w equals ui. Now, for this to make sense, we will of course require that uj is less than ui according to the cone order. So in the special case that we have an increasing sequence in the order structure, we can then talk about whether it's Cauchy or not in more or less the usual way. So having done that, we can now define an order theoretic notion of completeness. So we say an omega complete normed cone is a normed cone such that if you have an increasing sequence with bounded norms, then the least upper bound of that increasing sequence exists and it interacts well with the norm in the cone. So the least upper bound of the norms of the elements is the norm of the least upper bound. So convergence in the sense of norm and in the order theory sense match up in this instance. And Selinger actually proved a convenient lemma that says if you have an omega chain, so omega chain means increasing in the order, where the least upper bound in an omega complete normed cone. And then if you take any upper bound for that, if you have convergence in the analysis sense in terms of the norm, then that element has to be in fact the least upper bound. So basically we have a nice matchup between norm convergence and order convergence in this normed cone setting. We're going to define omega continuous linear maps between cones as one that preserve least upper bounds of countable chains. So this doesn't seem like the notion of continuity that you might be used to from analysis, but it is the notion that, for example, computer scientists doing programming languages are familiar with. They call this thing Scott continuity. And it's actually a different notion of continuity coming from a different topology. But because of these things I have mentioned before, it actually implies the norm continuity as well. Okay, so one can define bounded maps between cones in the usual way, and one can introduce a norm of a bounded map. You can make a category of these normed cones. So you take omega complete normed cones along with omega continuous linear maps, which we will call omega CC. And there's an interesting subcategory, which is where the norms of maps are all bounded by 1. So in this subcategory, isomorphisms are always isometries. So given an omega complete normed cone, we can define its dual to be the set of all omega continuous linear maps from C to the non-negative reals. And we'll define the norm on this dual to be the operator norm as we did it in the Banach space setting. And the basic fact is this will also produce an omega complete normed cone when you do that. So there's a nice duality functor that says if you've got a map between cones, then you get a contravariant functor star that takes you to a map between the dual spaces in the opposite direction. And this is very analogous to how you learn duality in algebra. So how does all this compare with the Banach space setting? So in fact, this dual is stronger than the usual dual in Banach spaces, where we only require the maps to be bounded or norm continuous. For instance, it turns out that the dual of L infinity plus, I'll define what this plus means later, is in fact isomorphic to L1 plus, which is not the case with the Banach space L infinity. So this is, in fact, we kind of independently discovered this, but later on we found out that people doing representation theory of C-star algebras knew stuff like this. And subsequently, John has also pointed out references in analysis books where people have studied exactly what is the dual of L infinity. So let me summarize the cones that we're going to use. If you have a measure on X, then we have the spaces L1 and L infinity that I defined before. Now we're going to restrict these things to be cones by considering the almost everywhere positive functions. And so these are the cones that I'm going to call L1 plus and L infinity plus.
Prakash, some people are wondering why you suddenly have been talking about cones so much. And I told them that it's because measures form a cone. Maybe you have your own
measures form a cone,
answer.
But perhaps more importantly, it's this fact. The dual that you get by introducing the cones, which then automatically brings in this order structure, allows you to talk about omega continuity instead of norm continuity, and then you get this duality between L1 and L infinity.
But I guess you could say that cones become really important whenever you're studying vector spaces with an order, and in probability theory, you really, the non-negative functions are really better than your average functions. You really care a lot about the fact that probabilities are non-negative, and so cones naturally show up in probability theory.
Good.
That's sorry. I'm just there's a bunch of people who are wondering why, what happened here. We started doing some probability theory, and then we got a massive invasion of cones.
the invasion of the cones. Yes. So, right. So perhaps it's always good to pause and you know, recheck our motivations. But for me, this thing that's on the slide now is very important, that this duality is perfect. But indeed, at a more basic level, things are cones when one is working with measures, because you know, you're working with things that are positive. One can say that, well, people do argue with me about this, because lots of people say, well, I can always artificially add the negative piece and make it embedded in a vector space. And sure, you can do that if you really like vector spaces so much. But talking about cones is nothing more than talking about order in a vector space anyway. And I think that's the significant point. So the cones that I'm going to talk about are these cones L1 plus mu and L infinity plus, which are both complete norm cones. So here are some more cones that we're going to use. So let me talk about this carefully. This, there was kind of a circularity in the notation here. So I'm going to use some notation which I'll define in a minute. But supposing I've got a measure space with a finite measure P. So I understand normally we're talking about probability measures, but in order to get a sensible cone, I need to talk about all finite measures, because of course I need them to be closed under multiplication by positive scalars. Fix a measure P on this space X and look at all finite measures that are absolutely continuous with respect to P. In a few slides, I'll define absolutely continuous, but it means P is absolutely continuous with respect to Q if when Q says a set has measure 0, P has to say it measures 0 as well. So that is it's kind of a bounding condition on the cones. And if Q is such a measure, we simply define its norm to be its total mass. And this thing is also an omega complete normed cone. And in fact, this particular family of measures forms a cone which is isometrically isomorphic to L1 plus XP. So that is actually not an obvious fact. Another family of cones coming from measures is obtained in the following way. So you have a fixed measure P. You look at all the measures that are uniformly bounded. That's what this UB stands for. Uniformly bounded by P. This means that there is some constant K such that for any other measure Q in this set, Q is below K times P. And this inequality between measures, of course, means that holds on every measurable set when you evaluate it. So this is, again, a complete normed cone. And this cone, MPUB, is isomorphic to L plus infinity. So you see there's a correspondence between these cones of measures and these cones of functions. Now there's a Reeds-like theorem which says the following. If you look at the dual of the cone L plus infinity, this is isomorphic to M bounded in this sense by P, cone of measures bounded by P. And a corollary of this is that if you look at this cone, we've already observed that it's isometrically isomorphic to L1 plus. And so immediately this theorem tells us that L1 plus is isomorphic to L plus star, L plus infinity star, the dual cone. And of course, this is the fact which is false in the general context of Banach spaces. There's another duality theorem which says if you look at L1 plus and look at its dual cone, then that's isomorphic to these things that are uniformly bounded by P, the collection of measures uniformly bounded by P. And again, we have the corollary that L1 plus star is isomorphic to L plus infinity. these isomorphisms are actually nicely expressed through a pairing function, which takes a product of the cones L plus infinity and L1 infinity to R, and it's simply defined by, you take the two functions, one from L plus infinity and one from L1 infinity, sorry, L1 plus, and you multiply them and integrate them with respect to P. So this very simple pairing actually mediates all these isomorphisms. This map is bilinear, continuous, and in fact, omega continuous in both arguments. So the duality I was alluding to earlier is simply captured by this pairing. So there's the isomorphism between L plus infinity and L1 plus star. That isomorphism simply takes a function f in L plus infinity and sends it to this linear map. And what's the linear map? It says, give me a g, multiply f and g and integrate the product with respect to p. So this is the element of L1 plus star that corresponds to the corresponding element of L plus infinity. So let me summarize these cones. We have the cone of measures that are absolutely continuous with respect to P, L1 plus X, integrable almost everywhere positive functions, and L plus infinity star, the dual cone of the cone of almost everywhere positive bounded measurable functions. These are all iso. And the other group is the upper bounded, uniformly bounded by P measures, the L plus infinity cone of everywhere, almost everywhere positive functions, and and the dual cone of L1 plus, namely the cone of almost everywhere positive functions in the norm vector space. This relationships between all these things are captured nicely in this diagram. So the vertical, the vertical arrows are all dualities. The horizontal arrows are all isos. So here you can see the duality between L plus and L1 plus and L infinity plus star. These things are iso, and similarly down here. So we don't have such a nice picture in standard Banach space theory. Okay, so I did introduce some words that I should have explained before, but I'm going to explain them now. Given two measure spaces, measurable spaces, and let's say you have a measurable function f between them. If you have a measure on the first space, then you can push it onto the second space. And the way you do that is you pull back a measurable set using f inverse and measure it in X using the measure that you have P. So this thing is called the image measure, and I'm going to write M sub F of P. So it's the measure that I get on Y lambda by pushing this measure along the measurable function F. When we say that a measure nu is absolutely continuous with respect to another measure mu, if for any measurable set, mu of A being 0 implies that mu of A being 0. And we write this slightly misleading notion because it somehow gives you the impression that nu is much smaller than mu, but actually it doesn't mean that. It could be a lot bigger. It's just that mu cannot assign a non-zero measure to a set if mu is assigning a 0 measure to it. If we have finite measures, then there's a kind of epsilon delta version of this definition, which perhaps makes the phrase absolutely continuous more palatable. But I don't want you to stare at this particularly. This notion will be good enough for us. There is a marvelous theorem called the Radon-Nikodym Theorem, which says that if I've got a pair of measures and nu is absolutely continuous with respect to mu, where these are both finite measures on a measurable space, then there is a positive measurable function h such that if you want to know the nu measure of a set, you can find that out by integrating h along over b using the other measure mu. So this is kind of a relationship between the two measures, and it's very evocative of a derivative. And indeed, one uses the derivative notation. One writes d nu divided d nu over d mu. Since mu is finite, these things will actually live in L1 plus x. And as John already pointed out, the functions that arise naturally are all positive. So they actually live in a cone rather than in a vector space. So this is the Radon-Nikodym theorem. It actually works more generally than what I have said. I've said finite measures. It actually works for so-called sigma finite measures. So given an almost everywhere positive function f, I'm going to use this notation f dot p to be the measure which has density f with respect to p's. It's kind of the opposite of the Radon-Nikodym theorem. And so two identities that we get are, if I take the Radon-Nikodym derivative and then I use that as the function whose density with respect to p I'm computing, I'll in fact get exactly the measure q. And conversely, if I take f dot p and ask for its Radon-Nikodym derivative with respect to p, of course, I'll get f. So these two identities just say these operations are inverses of each other as maps between L1 plus and this M thing, the space of finite measures that are absolutely continuous with respect to P. Okay, let me go back now after dosing you with all this functional analysis and a bit of measure theory. Let me go back and reconsider expectation and conditional expectation. Expectation of a measurable function with the underlying measure little p floating in the background is just the integral of f with respect to p, and therefore it's just a number. The conditional expectation is not a mere number, but a random variable, as I described before, and it is meant to measure the expected value that you are now re-estimating in the presence of additional information. So this additional information takes the form of a sub-sigma algebra, say lambda of sigma, and the experimenter knows for every set in this new sigma algebra whether the outcome is in B or not. So given this information, how is she going to recompute the expectation values? And this is how you do it. So given a measure space with P a finite measure, and supposing f is an L1 function and lambda is a sub-sigma algebra, then there exists an L1 function g, but notice where g lives. It's an L1 of x lambda p, not x sigma p, such that for all b, if I want to compute the expectation value of f over that b, I can do it by using g instead. And the key point to note here is that g is only required to be lambda measurable, not sigma measurable. Okay, so this function g is what is usually denoted by E f given lambda. So we clearly have f dot p is absolutely continuous with respect to p. So the required g is simply computed by the Radon-Nikodym derivative. Now, what are the properties of conditional expectation? The point of requiring lambda measurability is that it smooths out variations that are too rapid to show up in lambda. The conditional expectation is linear and increasing with respect to the pointwise order, and it is defined uniquely p almost everywhere. In short, not unique, but where it differs is only on a negligible set. Okay, so I'm going to introduce a couple of categories where the action happens. So I'm going to call these categories rad infinity and rad 1. This rad is supposed to suggest Radon-Nikodym. And this is going to be the source of the functor that defines conditional expectation. So the reason we have two categories is there are going to be two versions of the theory, a kind of L infinity version and a kind of L1 version. And going to go between these versions, duality will turn out to play a key role. So let me define carefully the infinity category. So this has objects, probability spaces, so that's sets, sigma algebras, which I'm suppressing, and measures, and measurable maps. And now the measurable map is going to have this following restriction. There's a measurable map alpha going from x to y, so I can push the measure p along alpha, and I'll get the image measure of p now living here, and I can compare it with q. If it happens that it's bounded by some constant times q, then we'll accept it as a morphism in our category. Okay, so to recap, the morphisms are measurable functions with the property that the image measure of p under that map alpha is uniformly bounded by the measure that's here for some constant k. The reason for choosing the name rad alpha is that if you take alpha in this category, rad infinity, then it maps to an element of L infinity plus. So that's the map I get by taking the Radon-Nikodym derivative of the image measure with respect to the measure that's in the target. Okay, so analogously, there's a category which we'll call the one category. Cis has objects, probability spaces, and arrows again are measurable maps. But now what I'm requiring is that if you look at the image of the measure under this measurable map and compare it with Q, the image measure has to be absolutely continuous with respect to Q. And the reason for choosing the name RAD1 this time is that if I take a morphism alpha in RAD1, and then I look at the Radon-Nikodym derivative of the image measure along that map, I will get something in L1. So these are the two categories. The fact that the category rad infinity actually embeds in RAD1 reflects the fact that the L infinity plus spaces embed in the L1 plus spaces. So remember the pairing function? So for example, if you're going from L infinity plus to L1 plus star, then the pairing function works like so. You take an f in L infinity plus, and you map it to this linear map. And the linear map does what? It takes a g in L1 plus and simply multiplies the two functions together and integrates it with respect to p. So that's the pairing that's mediating the isomorphism between L infinity plus and L1 plus star. Okay, let's go back and look at a very elementary thing, namely precomposition. So precomposition with alpha and rad infinity gives a map which I'll call P1 alpha. It goes from L1 plus y to L1 plus x, obviously in the contra direction. Dually, given alpha in rad1 from x to y and g in L infinity plus y, we get a P infinity alpha g that lives in L infinity plus x. Again, you see the direction has gotten flipped. So the subscripts on the two precomposition functors describe the target categories. Now, using the duality functor, the one that gives you the dual cone, we've got a map P1 alpha star. And now this one goes from L1 plus star to L1 plus star. But now you see it got flipped again. So alpha went from x to y. Precomposition with alpha went from y to x. Starring it has you going back from x to y. And dually, if you use P infinity alpha star, you go back from L infinity plus star of x to L infinity plus star of y. Okay, so now they're going in the same direction that alpha was pointing. And now finally, we're ready to define expectation values. So the functor E infinity is a functor from rad infinity to omega cc, which on objects, so an object in rad infinity is just a space with a sigma algebra and a measure, to the omega complete normed cone of L infinity plus of xp. And on maps, it's given as follows. So given an alpha from x to y in rad infinity, we're going to produce a map from L infinity plus x to L infinity plus y. And how are we going to do this? We're going to compose P1 alpha dualized with the isomorphisms between L1 plus star and L infinity plus. So these things are not easy to see unless you look at a commutative diagram. So let's follow it around. I want to define an expectation value like this. So I've got an alpha going from x to y, a morphism, and I want to say, aha, now I'm going to define conditioning with respect to alpha rather than conditioning with respect to a sub-sigma algebra. And how do I do it? Well, I start out here, L infinity plus x. The canonical pairing takes me to L1 plus x star. P1 alpha star takes me to L1 plus star y. Right? Notice it's in the same direction now because I've done two contravariant things, precomposing and starring. And then the isomorphism brings me back here to L infinity plus y. So what have I done by going around the circle? I've defined a map like this from L infinity plus X to L infinity plus Y. And using the pairing, you can write down formulas for it. This is the thing that we're going to call the expectation value functor, which takes a morphism from X to Y and produces a map from this space of functions to that space of functions. Now, there's a very interesting calculation you can do. It's very easy, but it tells you that if I compute this pairing, which kind of looks a bit like, at least notationally, like an inner product, if I compute E infinity alpha F with Y, if I compute this pairing, it turns out to be equal to exactly that pairing. And you can just see this by following the isomorphism around the picture. And for this reason, we say, oh, this is kind of like a left adjoint, not left adjoint, of course, in the category theoretic sense of adjoint functors, but more like adjoint as we might have learned it in Hilbert space theory. But you see that when I take the E infinity alpha F on the left and pair it with G, it's the same as taking F, plain and simple, and pairing it with the precomposition of alpha and G. Right, so we started with an alpha and rad infinity. We get the expectation value as a map between L infinity plus cones. The other
Can I ask what you mean by we can informally view it as a left adjoint? We have a lot of category theorists in the audience who would like an honest left adjoint, if possible. But what do you mean by that?
I just mean if you look at, gosh, I'm trying to figure out how to go backwards. There we go. So if you look at this equation, I just mean if you look at this equation between the two forms of the pairing, I mean, this was heavily put in quotation marks, yes, it was. And I did try to say it's not a left adjoint in any categorical sense, but it looks like, if you think of this as something analogous to inner products in Hilbert spaces, it does look like an adjoint to precomposition. That's all I mean. Maybe it's a misleading concept.
So you're using the analogy between this pairing of vector space,
yes,
a Hom set between objects to set up an analogy between these type of adjoints and adjoint functors. Yeah.
Yeah. If there's really a left adjointness thing happening, I haven't seen it yet. But okay. So the other expectation value is obtained in a very similar way. You start out in L1 plus X, you go to L infinity plus star through the pairing. You use precomposition dualized. That gives you a map from L infinity plus star X to L infinity plus star Y. God, I need better names. And then again, you use the isomorphism mediated by the pairing to get you back to L1 plus Y. And in the end, this going around the loop defines the map E1 alpha from L1 plus X to L1 plus Y. Once again, we have a adjointness statement. I did put quotes everywhere you see. This time it is a right adjoint because you can do this simple calculation. And you see now the E1 appears on the right and the P infinity precomposing with the morphism alpha appears on the left. Whether this means anything or not, probably not, but we just thought this was an amusing fact. The two expectation value functors are actually related in this way. So you can actually find a relationship like this. So if I take E infinity alpha of the identity function on X and apply that to F, it's the same as applying E1 alpha to F composed with alpha. And similarly for the other way around. So these are just calculations one can do that hook these expectation value functors together. Anyway, so the key point about these expectation value functors is that they allow you to go from one space to another related through this by this morphism alpha, and that alpha need not just be an inclusion of a subsigma algebra and a larger sigma algebra. It could be something else. So it generalizes the notion of just having the inclusion of a subsigma algebra to more or less an arbitrary morphism satisfying some conditions on behaving nicely with respect to the measures. Okay, so I'm almost at the end of my time. So I'll end with this. This looks like something that we just did because we could, but it wasn't like that. What we were really trying to do is work out how to approximate Markov processes. And so what we were doing is we said, look, we have a Markov process, which is defined by a Markov kernel. And what we wanted to do was to say, I now have a cruder version, an approximate version of this Markov process. And the way we were approximating was to say, well, we may keep the same old state space, but we'll have a much coarser sigma algebra. So in that sense, kind of coarsening the information. And now we wanted to say, all right, then all those kernels that we had before, which are just parameterized measures, we need to have the coarsened versions of them. And to compute those things, we needed exactly this technology from conditional expectations. So the key point here was that a lot of people do approximation by saying, let's take this big state space and lump it together into chunks, and then kind of view things as happening between chunks instead of between points. But now what we did was we said, okay, the notion of approximation is not chunking the pieces of the state space, but rather looking at cruder sigma algebras. And then perhaps as we are refining it, we get more and more refined sigma algebras. So there was quite a lot of stuff we did there. We defined projective limits of families of Markov processes, and we
did you get a new Markov process from an old one? That is the semi-group law of a Markov process. Does that still, do you still get that?
We did get Markov processes, but I should say these were discrete time things, even though continuous space, but we were only looking at discrete time. So
well,
we didn't.
So you, yeah, that's still interesting and non-obvious that you could say,
but
you have a sort of a canonical way to coarsen
yes. So
a given map. Yeah, okay, maybe I see that. That's interesting.
Right. So we haven't done this for continuous time processes where you would want to verify the semi-group law, but we did do the analogous thing, which is I think called the Chapman-Kolmogorov equation, but it's just composing Markov kernels. And that's where functoriality became important.
Right. So coarsening and composing is the same as composing and then coarsening. That's
exactly
the idea.
Exactly,
yeah. Right.
That's
Great.
exactly the point.
Yeah, that's cool.
So, so in fact, I would say this was in some sense the easier part of that long paper. But since you didn't give me 5 slots, I won't, I won't talk about this. But I thought this was a kind of a nice piece that could be extracted from that. It's actually only a few pages of that long paper, which is 45 pages long. Okay, so I think that's it. All that stuff is the subject of actually probably 2 or 3 different talks, which I don't want to give now. I actually gave a whole series of talks on this at Lumini in Marseille, I think 8 years ago, and those slides are on my webpage. But anyway, that's it. That's I'm on 1:55, so I think I've used up my 55 minutes, and I will let John moderate the question session.
Okay, thanks very much. I'll applaud. People can applaud either virtually or, yeah, there are different, different ways to applaud. High-tech ways to applaud. I haven't figured out how to make that little clap sign that Kartik just did. I'm not.
Kartik did a clap sign.
Now you should turn on the chat if you want to see lots of people cheering you.
Okay, I'm not sure I know how to do. So I have to stop the share? Is that what do I do?
I don't think so. I don't know. Maybe you can. At the bottom of your screen, there should be a little thing that says.
So there's
chat.
nothing. There's nothing on the bottom of my screen. On the top.
Oh well, you better stop the. I don't know. Then I guess you need to stop the share.
Okay, let me stop the share. Ooh, now I see everyone.
Okay, see, you see that like you're talking to a huge throng of people.
Gosh, all of them I didn't realize were there.
Okay.
So I see all kinds of people. Joachim Koch. Hi, Joachim. And some of my students from McGill and so on. Yes, Tobias. Hi, Tobias. Anyway, sorry, go ahead.
Yes, so does anyone have a question? If there are relatively few people who are dare to ask a spoken question, you can just unmute yourself. Oh, okay, well, here's someone types in a question into the chat. Do you see that, Prakash?
Yes, I'm trying
I
to.
was wondering whether the category omega CC relates to the category of probabilistic cones studied by Erhard, Pagani, and Tassone.
Yes, closely related. So I think those guys are working with with Reed lattices. So that's kind of vectorizing the cones that we have. So yes, they're very closely related. In fact, I think they're almost the same thing. I think Tom Leinster has his hand raised, so maybe you can go ahead, Tom.
Oh, hi. Thanks for the talk. That was great. I have a question about slide 21. Are you able to get that back up again?
Yes, I'll have to do sharing again, I think. Sharing. Yeah. Okay. So has that happened?
Nope.
To me.
Yes.
Now, yes.
Yeah.
Okay. Slide 21. Wow, that's way back there. Okay. What I don't know is how to get there quickly, so I'll have to go.
That's okay.
21. Yeah.
Or you say that the cones M and L1 are isometrically isomorphic. And I think you mentioned that that was non-trivial. Is that right?
Yeah, I don't know what you mean by non-trivial exactly. It's doable. I mean,
It's it's
not
largely
obvious.
the Radon-Nikodym theorem, right? I mean, it's not trivial in the sense that that's not trivial.
It's not just Radon-Nikodym. We had to work a bit more, but
So what kind of thing goes into that?
We actually constructed the isomorphism explicitly and verified it.
This paper is 7 years old.
No,
Yeah.
it was 11 years old.
Okay. Real question. I'm sorry.
I honestly don't remember exactly.
But I think if you have a finite measure that's absolutely continuous with respect to P, then it will be a positive L1 function times P that's Radon-Nikodym. And
Yes,
I
that's
think is sort
Radon-Nikodym.
of a key aspect of that.
Yeah.
Because you have to check that gives you an isometric isomorphism.
Okay. Okay, thanks.
So I'll stop sharing again in case.
Okay, there's well, someone just asked, Archer just asked a question about slide 41.
Yeah, I don't know if you feel like going, you just went back, now you have to maybe go forward. But so on slide 41 and the consequences towards the very end,
Yes.
you wrote down two equations that look like adjoints. And these equations look like they're essentially Bayes' theorem. Do you have any comments on that? It just reminds me of an equation that I would normally associate with Bayes' theorem.
This one, for example.
Yeah, yeah.
That's Bayes' theorem, is it? I didn't see it like that. Can you tell me why?
Well, so in terms of, so you're familiar with, I mean, your disintegrations, right? So this idea of you start off with some alpha, which is just your measure preserving map on some measurable space. And then this expectation function looks like the disintegration of that map, right? Mm-hmm. Is this roughly the idea for the expectation map? Or am I?
We didn't use the disintegration theorem anywhere in this. So you're saying it looks like the disintegration of what with respect to what?
It looks like well, I mean, in the case of your sub-sigma algebra, you have an inclusion, right? It's the identity function because one sigma algebra is larger than the other. So that's a measurable map. And you have a measure on one of those spaces, on the domain space. And so that gives you the data you need to ask if disintegration exists.
Mhm,
And this integration is essentially just a
right, yes.
like a stochastic map in the opposite direction, but you're viewing it on the function side. So that
Yes,
would correspond to a positive linear map in the
yes,
other direction.
yes.
And the equation you wrote down here looks very similar to, it's maybe just the notation is throwing me off, but it looks just
But
like
you could be right. At the time that we wrote this, as John said 11 years ago, at that time I didn't know much about disintegration at all. But since that time, I have spent quite a lot of time disintegrating. So I need to relook at it from that point of view. I think that's an interesting remark.
Mhm.
But
I think it's actually very interesting that you found two different, a left and a right one.
yes.
Because I've actually been looking at this in the quantum mechanical context, and I've also noticed that there's a slight distinction between these two sides. But again, I'm not sure if it like formally looks just like the same equation, but I don't know exactly.
Quantum mechanical setting, what are you doing? Working with von Neumann algebras or something?
Just for now, finite dimensions to avoid as much trouble, but eventually, yeah.
I'd love to hear about that.
Thanks.
So if you have some note or something, you can email me. I'd love to see it.
Sure. Thank you. Yep.
Thanks.
So there's a question from, which is already beginning to slide off my page, from Hannah Oppelmeyer on the chat.
I'm keeping, so if she speaks, I guess she will pop up on the chat window.
She can, well, I mean, I'll read her question, or I'll read it, and then she can read it if you have a question. For conditional expectations for sigma algebras, which are not nested, I mean, I guess one is not a sub-sigma algebra of another, there is not always a limit which can be realized as a conditional expectation with respect to some sigma algebra. I don't quite understand that. Do you think your generalization could help that?
Right. So I think so, because of course, we need the alpha to have the right properties, yes? So the image measure has to be absolutely continuous with the given measure. But if you have a situation like that, even if the sigma algebra here is not exactly a sub-sigma algebra of the other one, you should be able to define a conditional expectation. I think Tom has his hand raised again.
I'm unable to see those raised hands, so, but go ahead.
No, sorry, mate. I can't lower it for some reason.
Oh, I see.
You got a stiff arm, Tom?
Yeah, it's stuck.
So, Tom, are you in Edinburgh or Glasgow?
I'm physically in Glasgow because that's where I live.
I see.
But mentally?
Yeah, mentally I'm in Edinburgh.
Well, I'm going to be spending time in both of those cities as
Great.
soon as I'm allowed to travel again. So I would love to talk to you.
That'd be fantastic.
Any other questions? Other question, Paulo, can we find the stuff about dunes in the mentioned paper?
Sorry, I lost your audio for a second, John. Can we find what?
I'm just in the chat. Paulo asked, can we find the stuff on dual cones in this paper you wrote?
Yes, you can. So all that is written in detail, including all these proofs of all these claims of isomorphisms and equivalences and dualities.
Mm-hmm.
I would have probably served me better to read these proofs again last night. Instead, I was looking for an explicit example of something that's in L1. Sorry, there's something that's in L infinity star, but not in the image of L1. And only after a lot of time, I found out that it's very hard to write down such examples.
I was wondering about that. I thought they might only be constructible using the axiom of,
yes, that's correct.
of choice.
You can
yeah, so it would be very interesting to try to look for some alternate axioms of set theory in which the dual of L infinity becomes L1, just like how, so like, sorry, what's his name? Blanking out on names, but people showed, for example, that there's extensions of ZF set theory that in which all subsets of the real line are measurable.
Solovay.
Yeah, Solovay.
Right. So in fact, in other
Senior.
research that I'm doing, I'm looking at Boolean valued models of set theory with the purpose of giving semantics to the stochastic lambda calculus, which is lambda calculus enhanced with some probabilistic features. And we're using, so various people have been studying this from different points of view. But our point of view, which is really pioneered by Danos Scott, is to look at the standard kind of models, set theoretic models of lambda calculus, but interpreted in a Boolean valued model of set theory. And for the Boolean algebra, you use the measure algebra. So it kind of gives it a probabilistic flavor. So in fact, I remember Dana saying, you should have been doing all this with Boolean valued models of set theory. One of these days I'll do that. That's, yeah.
Any other questions? So let's thank, so let's thank the speaker again. And I think I'm going to grab a cup of coffee and then I will repair to the Zulip discussion room, right, where people may already be talking about Prakash's talk. So when I gave, and here's the location of that in the chat window, you have to be a member.
Okay, well, thank you very much for listening. I see there are